We'll have to clean the filter. So this was something that I didn't want to take away from your coffee break, at 3:30 to go into, but I thought it's something useful. You've seen this plot on the right-hand side several times, just showing the particular x values that you would need to produce a certain mass at a certain rapidity. And it's sort of very useful to be able to look at this and say, okay, if I want to produce a mass of 100 GeV at a rapidity of 2, these are the x values that I need. But it's not quite complete, because what you'd also like to know is what is the PDF luminosity for those particular kinematics. You can define that, dl, ij, ds hat, dy, just the product of the two PDFs at a particular, x1 and x2 value to produce that mass and that rapidity. And then you can define a cross-section. You usually define it using this kind of formula here, but you can also define it in terms of this differential luminosity, integrated over y, for example, if you're not interested in a particular rapidity value for the mass of the state you're producing, times the scaled cross-section, s hat times sigma hat ij. Now these luminosity, okay, and here I've integrated over y, dl ds hat, that's something you can calculate. You can calculate individual PDFs, you can calculate the product of individual PDFs. So there's 3 curves that are shown here for the LHC, and the blue curve gives the gluon quark luminosity at the LHC as a function of the square root of s hat of the state you want to produce. The green gives the blue luminosity, and the red gives the QQ bar. And so, for example, if you wanted to know, what is the rate for gluon pair production for square root of s hat of 1 TeV, and for a mass range delta s hat of 0.01 s hat, then you can read off from here that the blue luminosity is equal to 1,000. Then now you have to multiply that by a scaled cross-section that's shown over on the right. And these have particularly simple forms, right? They're just constant values. So if I look up at blue goes to blue, that's 20. So that tells me the cross-section is going to be 200 picobards. This is kind of a lookup table, right? If you just want to, calculate something very quickly. Now, if you look at the curves, you can see that, they're not just single lines, they're bands. That's the PDF uncertainty for those luminosities. Of course, it's not so useful on that scale, but, they also have the companion plots showing linearly what the uncertainty. Here, for example, is blue luminosity uncertainty. And you can see that the blue luminosity is very well determined until I get the masses at the LHC above a TeV. Then it blows up, because even with the jet data from the Tevatron, we still don't know what the high X gluon looks like. And you can also define it for specific values for rapidity. So all of those are in the talk and in the paper. And here are just the luminosities defined for specific rapidity values. Now, one of the interesting things is to go from the Tevatron to the LHC. So, for example, suppose I look at the ratio of the luminosity for a particular subprocess, initial state, at the LHC compared to the Tevatron. So I come up with a family of curves. So the green curve, this is using the same color scheme. The green curve is the ratio for blue. So blue at the LHC compared to blue at the Tevatron. The blue is gluon quark at the LHC to gluon quark at the Tevatron. And the red is QQ bar at the LHC compared to QQ bar at the Tevatron. So you notice that one of these curves is not like the other. And that's the QQ bar, because there's not as big an enhancement at the LHC, because Tevatron has these valence antiquarks that are available. What's that?
Pointer.
Oh.
Red one.
So the Tevatron has valence antiquarks, and so the enhancement factor, until I get above 500 GeV or so, is only a factor of 10 or less. So suppose that I have a signal, some new physics like Chargino pair production that proceeds by QQ bar. In that case, I'm going to have an enhancement factor, that's, again, something between 5 and 10. But on the other hand, if I have a background that has a gluon quark initial state or glue initial state, that's going to have an enhancement factor of 500 or even 1,000, depending upon the mass of the state that I want to produce. So a specific example, suppose that I look at TT bar production at the LHC. So TT bar production at the LHC is mostly through glue, with a little bit of a QQ bar component. At the Tevatron, it's reversed. It's mostly QQ bar with a little bit of glue component. But on the other hand, W plus 4 jets. Oops, did I push the wrong?
No.
No. But on the other hand, W plus 4 jets, which is primarily glue on quark at both the Tevatron and the LHC, that gets a very large enhancement factor of 500. And so whenever I go from the Tevatron to the LHC, I have a very small glue component at the Tevatron being multiplied by a large factor. And I have a very large QQ bar component being multiplied by a very small factor. So the end result is that the background for TT bar production at the LHC is going to be a lot larger than the background for TT bar production at the Tevatron. Of course, you have to do something to make up for that. And what the experiments have done is to increase the cuts they make on the jets in the final state. So instead of having 15 GeV at the Tevatron, they have cuts of 30 to 40 GeV. That comes at a price, right? Your efficiency is going to be reduced. But luckily, the cross-section is so high and the luminosity is so high, you have so many TT bar pairs that are produced that you can afford the cut that you take by requiring these higher PT cuts in the jets. All right, that's my 5 minutes worth. And it was worth staying for, wasn't it?